Hello everyone. So today we are going to start a new topic, of course on torsion, but it is going to help us in understanding how to obtain or solve the torsion problem for a shaft with arbitrary cross section. So this is called membrane analogy. So this is not a new theory. It is just a method by which we can solve torsion problem with much more ease. So this was proposed by Prandtl, the same Prandtl whose stress function we have studied in the earlier lecture. So to start with, let us imagine a thin membrane. So let us imagine a thin membrane whose cross section or whose shape is same as the cross section of the shaft for which we are studying the torsion problem. So the first thing that we have to imagine is that the shape of the membrane shape of the membrane is same as the cross section of the shaft under torsion. The second point about this membrane is that the membrane is supported all along the edge. Okay. So, it is supported all along the edge. So, along the edge there would be no out of plane deformation. So, let me also add to this, imagine a thin membrane in the xy plane. Okay. So, it is supported on the edge so that the outward deformation, that is the deformation in z direction along the edge is equal to 0. Now, the third point is that a uniform tensile force N per unit length is acting along the edge. In normal direction. So, along the edge there is an in plane, so uniform in plane tensile force. So, this is going to be in plane tensile force. So, in an uniform in plane tensile force of N per unit length is acting along the edge in the normal direction. That is the third point. The fourth point is that uniform pressure of Q per area is acting on the membrane in z direction. Okay. So right. So this is the these are the features or properties of this membrane. So we have to consider a thin membrane. The shape of the membrane is same as the shape of the cross section of the shaft. The membrane is supported all along the edge. A tensile force in normal direction and in plane tensile force in normal direction of the magnitude n by unit length is acting all along the edge of the membrane, as well as there is an uniform pressure of Q by per unit area acting on the membrane in the z direction. So, let us now try to draw this membrane. So, how is this membrane going to look like? So, of course, the shape is going to, so this is x, and this is y. So, all along the edge there is a force in the normal direction which is n per unit length, that is acting all along the edge of the membrane, and this entire edge is supported so that there is no out of plane deformation of this edge. Okay, so this entire edge is supported, and the shape of this membrane is same as the shape of the cross section of the shaft. Now, and then the other thing is that the uniform lateral this is x, this is z, and this is Q per area. Okay. And so likewise here there is n and here there is n. Okay. The H force N is also acting, and the uniform pressure of Q by area per unit area is acting on the membrane. So, this shows the deformed. So, this is the deformed shape of the membrane because of the applied uniform pressure. Now, let us try to see what are the equations of equilibrium for this membrane. So, if I assume a small elemental area on the membrane, this is dy and this is dx. Let us find out the force equilibrium or equation of this elemental area in the z direction. So, I need to find out Okay. So, let me draw the elemental area. Okay. So, what I have done, I have drawn the forces on the elemental area defined by dx and dy in the plane xz, in the xz plane. So, now let us see. So, what is happening? So, this black color is the portion of the membrane. So, the two H force N is acting at the two end of this elemental portion, okay, and the uniform pressure Q is also acting on this uniform portion. Now, let us see if we try to find out the net force in the z direction, what are going to be the net force in z direction. So, before we move into finding out the net force in z direction, let us say that the displacement at this point is w, and therefore, at this point it is w plus del w by del x. Okay. So, the deformation in z direction, if it is w at this point, then it is w plus del w by del x at this point. Okay. Therefore, if I try to find out this angle theta here, and this is going to be 90 minus theta, and this is okay. And now, let me try to resolve the force in the z direction. Let me try to do that. So, what is the first force? So, let me take this force. Let me first take this force and see what is the component in z direction. So, I have that as minus n. N is the force per unit length. So, n into dy is the total force that is acting on the element in the given direction. So, n into del y is the total force, and I have to find out the component of that force in the z direction. So, that is going to be del w by del x, because this angle is going to be del w by del x. So, n into sine of theta. So, that is going to be n into dy into theta, and theta is going to be del w by del x. So, and the minus sign, because it is pointing in the negative z direction. So, that is coming from this force. Now, let us move into this force. What is the component of that? So, that is going to be plus n into dy, of course, and then I have del x by w plus del w by del x. Okay. That is going to be the angle at the sin theta of the angle between the z axis and the force n. So, similarly, so this is because of the force that is acting on the length dy. Similarly, there would be another set of force that is acting on the length dx. Okay. From there also we are going to get a component in the z direction. So, let me write that then in this form. So, the component that is coming from the force that is acting along dx, that is going to be minus n dx and then del w by del y plus n dx del by del y w plus del w by del y, right. So, this too comes from the similar force equilibrium or the similar force component in the z direction, plus there would be an upward force due to the uniform pressure Q, and that force can be written as plus Q dx into dy, dx into dy being the total area and Q being the force per unit area, and that has to be equal to 0 for the equilibrium of the elemental area in the z direction. Now, if I simplify this, you will see that this is going to simplify as n del 2 w by del x square plus n del 2 w by del y square is equal to minus q, right, because this is going to get cancelled out with this. This is sorry, not that, not this one. This is going to stay. So, this is going to get cancelled out with this and this is going to get cancelled out by this. So, I am going to left with n into del 2 w by del x square plus n into del 2 w by del y square. I can further write this down as del 2 w by del x square plus del 2 w by del y square is equal to minus q by n. So, this is the equilibrium this condition is what we are getting from the equilibrium condition of the elemental area of this membrane in the z direction. Okay. So, now let us look into this in carefully. So, this equation, just remember this equation. Okay. So, what is this equation analogous to? Can you visualize that you have seen a similar equation earlier in the context of torsion? Okay. So, let me try to draw the analogy now. Okay. So, the equation that I get, so for the membrane, so for the membrane I get this equation del 2 w by del x square plus del 2 w by del y square is equal to minus q by n, where w is the deformation of the membrane, w is the deformation of the membrane in z direction. Okay. When q is the pressure on the membrane, n is the in plane force, in plane tensile force in normal direction. force by length. Okay. Now, if you look into this equation, this is completely analogous to the equation for the Prandtl stress function. So, the equation for Prandtl stress function is del 2 phi by del y x square plus del 2 phi by del y square is 2 g theta. Okay. So, from this two expression we can conclude that the stress function for a shaft with an arbitrary cross section is same as the deformation of a thin membrane of the same cross section under an uniform pressure Q and an in-plane tensile force N acting along the edges. Okay. Now, this is a great experimental study that we can do. We can always have a thin membrane, we can always cut it out in the shape of the cross section of the shaft, support it along the edges and apply the tensile force and apply the uniform pressure. The shape of the deflected or deformed shape of the membrane is going to be exactly same as the Prandtl stress function for the shaft, provided minus q by n is replaced by minus 2 g theta. So, we have to choose q and n in such a way that it has to be equal to minus 2 g theta, then the deformed shape is going to be exactly similar to that of the stress function for the shaft. Now, we all appreciate that once we get hold of the stress function, then we can solve the torsion problem with much ease. I mean, the only problem lies is in finding out or getting hold of a stress function. So, once the stress function is obtained, our life is very easy. We can do anything, we can do any analysis of the shaft once we get hold of the stress function. So, we see the analogy between these two expression, as well as W is also equal to 0, is 0 on the boundary because it is supported on the boundary. And phi is also equal to 0 on the boundary. Right. So, not only the equations, the criteria, but also the criteria of W being 0 on the boundary is also satisfied. Okay. Therefore, we can say that if we can experimentally find out the deformed shape of the membrane, we can very easily obtain an estimate of the stress function. Okay. So, with this I will move into certain corollaries. So, this is not all. We will gradually see that the membrane analogy has several other advantages and has several other corollaries, which makes the analysis of torsion of a shaft arbitrary cross section much more easier. Okay. So, let us move into those corollaries. Okay. So, now again let us go back to the membrane and let us draw a contour on the membrane. Okay. So, this darker line, this lighter line, say it is a contour line for the membrane under the uniform pressure. So, for this contour line W is constant. Okay. Now, what we are going to do is that we are going to choose an arbitrary point B on the contour. Okay. And let me draw the normal. So, this is N, the normal direction, this is the tangential direction. Let me take an elemental length in the tangential direction and call it as ds. Okay. So, let me draw the Cartesian coordinates also. So, this is dx and this is dy. Okay. Now, so W is constant, which can also be said that del W by del S, S is the tangential coordinate, is also equal to 0. Now, what we do is that we find out the resultant of shear stress of shear stress at B in the which is on the contour line, okay, in the normal direction. So, let me just repeat. What we are doing is that we are drawing the drawing a contour line on the membrane, or the line that has the same deformation or deflection in the z direction, that is W is constant along the contour line, and therefore, del W by del S is equal to 0. Now, we choose an arbitrary point P on the contour, and N is the normal to the contour at that point B, and ds is an elemental length along the tangential direction of the contour. Now, what we are trying to do is to find out the resultant of shear stress at B in the normal direction. Okay. So, what is going to be the resultant of shear stress? So, let me call this angle to be theta. This angle, let me call it to be theta. Okay. So, the resultant of shear stress tau x z is into cos theta plus tau y z into sin theta. So, that is the resultant of the shear stress in the n direction. Okay. So, this is tau x z and that is going to be cos theta, and tau y z, which is in this direction, in the y direction, that is going to be sin theta, and both of them add up together. Okay. So, now let me express theta or sin theta and cos theta in terms of ds and Cartesian coordinate x and y. So, what is tau x z? Tau x z is del phi by del y. And what is cos theta? Cos theta is going to be dy by ds, right? We can see that, right? So, it is going to be dy by ds is going to be cos theta, and then tau y z is going to be minus del phi by del x, and sin theta is going to be minus dx by ds. Okay. So, this 2 cancels out and makes it a positive sign. So, this or this can be written as del phi by del y dy by ds plus del phi by del x into dx by ds, and that can be written as del phi by del s. Okay. Now, let us try to understand. See, phi is analogous to w, okay, and w is 0 along this del w by del s is 0 along this contour line. Therefore, del phi by del s is also going to be 0 along this contour line. So, this has to be 0 along this contour line. So, what does this mean? If del phi by del s is equal to 0, that means that the resultant of shear stress at this point in the normal direction to the contour is going to be 0. Okay. So, let me just write it down. Therefore, this implies that resultant of the shear stress in normal direction on a point on the contour line okay, right. So, this is an important conclusion. We will get to know about this, why this is useful a bit later more clearly. Okay. So, now let us go to the next step, that is we are trying to find out the resultant of the shear stress at B in the tangential direction of the contour. So, let me do that derivation. Let me just erase this off. Okay. So, let me try to find out the resultant of shear stress along the tangential direction. Of the contour. So, what is going to be the expression of the resultant of shear stress in the tangential direction? It is going to be minus tau x z into sin theta plus tau y z into cos theta. Okay. So, now this can be written as minus del phi by del y into dy by dn minus del phi by del x into dx by dn. dn is an elemental length in the normal direction. Okay. So, from geometry we can see that sin theta can also be written as dy by dn and cos theta can be written as dx by dn. Okay. So, therefore, the resultant, so this can further be written as minus del phi by del n. Okay. Therefore, if we want to summarize, then the shear stress, okay, the net shear stress at any point on the contour in the tangential direction is tau, which is equal to minus del phi by del n. Okay. Now, again phi is analogous to W. Okay. Therefore, del phi by del n is analogous to minus del W by del n. Now, what is del W by del n? So, what is del W by del n? Del W by del n is nothing but slope of the membrane at that point. Okay. Now, the why did we do all this analysis? Why we did all this analysis is to understand this, that the resultant of the shear stress at any point is going to be analogous to the slope of the membrane at that point. So, the maximum stress that will happen on the shaft is going to happen at the point where the corresponding or analogous membrane is going to have the maximum slope. See, let us try to reiterate again. So, one of the main purpose of doing the entire stress analysis that we are doing is to find out the maximum shear stress. Okay, because the entire design is going to be based on the maximum shear stress, because the maximum value of the shear stress that develop in the shaft should not exceed the ultimate shear strength of the material. Therefore, we have to figure out what is the maximum shear stress that is developing in the shaft, and we have to check whether it is below the ultimate shear strength of the material. Now, it is a very difficult task, even if we know the stress function, we know the shear stress distribution, it is a very difficult task to find out what is going to be the maximum value of the shear stress. But this gives you a very easy way, this membrane analogy gives you a very easy way to figure out at what location the maximum shear stress is going to happen. So, you can always visualize the membrane and you can visualize the deformed shape of the membrane. Once you visualize the deformed shape of the membrane, you can visualize at what point the membrane is going to have the maximum slope, right. We can all, from our intuition, from our understanding of mechanics, figure out at what point the membrane is going to have the maximum slope. So, that is going to be the point where the maximum value of the resultant of shear stress is going to happen. So, if we find out the shear stress from the stress function at that particular point, that is going to be the point, that is going to be the value of the maximum shear stress. Okay. That is a great ease in analyzing a shaft under torsion. Okay. If you do some more tutorial problem, which I will be posting soon, you will see that finding out the maximum value of the shear stress is a difficult task unless we use membrane analogy to find it out. Okay. So, with this we are going to move into the next corollary, that is to find out the relation between the torque and the membrane, the deformation of the membrane. Okay. So, Okay. So, we know that from the Prandtl stress function that the torque mt, torque or torsional moment mt, is equal to 2 phi del x by del y. Okay. So, now phi is analogous to okay. Therefore, mt can also be obtained as 2 times the volume of the membrane enclosed by the xy plane. Okay. So, if we know the deformed shape of the membrane, if we can find out the total volume enclosed by the deformed membrane by the xy plane, then that is equal to the torque that is going to act on the shaft, provided we replace q by n by 2 g theta. Okay. So, this is another corollary of the membrane analogy. Okay. So, with this we will conclude the lecture on membrane analogy. We will talk about this more, and when we solve the problem of finding out the shear stress distribution in a thin rectangular strip due to an applied torque mt using membrane analogy. So, till then let us conclude this